Well, there were 50 subjects.
Oh, 50 subjects.
50 subjects.
34.
But,
Yeah.
so all of the subjects were placed in a booth for an extended period of time and monitored by a hidden camera. 2/3 of the subjects were given a yawn seed. And, well, what's 2/3 of 50?
34.
Okay, so 34 were in one group. Okay, so 34 were in the group that got a yawn seed. What do you suppose that means?
Somebody yawned in front of
Somebody yawned in front of them. And then who was left? How many were left to be in the other group? 16 were left for no yawn seed. Say yawn a couple times and it's not a word. It does. It's like one of those words you're like, this is not a word. Okay. So we have two groups or two samples. And are these paired? Did they pair them together? No, because first of all, if you're pairing, you have to have the same number in each group. Okay? And it's not a big deal that we had more in the group that got a yawn seed than didn't. It doesn't matter. The groups don't have to be the same size. Okay, so how many in the group of 34 actually yawned? 10. So 10 out of 34 then yawned. So what is our parameter of interest? Parameter of interest.
People who yawn.
Okay, what about, how would you describe this value, 10 out of 34?
The number of people who yawn, what kind of
But the 10 over 34 is not in how many? It's a percent. It's a proportion. The title of this is called Comparing to Proportions. So the parameter of interest is the proportion of people who yawn. Now there's a little more to our parameter of interest because we're not just interested in the proportion of people who yawn. We would like to know,
who yawned.
well, we also want to know who yawns with no seed, because how many in that group yawned? 4 so there were still 4 people that yawned out of 16 that didn't have a yawn seed. So this percent is 0.9, well, this is 0.924, that's the fraction, the proportion, and this was 4 out of 16 is 0.25. Okay. So the question is, does a yawn seed make people yawn more than no yawn seed? So it's actually, we're not just looking for the proportion of people who yawn, we're looking at the difference in the proportion of people who yawn between our two groups. So that's what we're interested in. We're interested in the difference between the proportion of people who yawn given a yawn seed or not given a yawn seed. Does that make sense? Okay. So what this type of test is called, since we're dealing with proportions, this is going to be called a two-sample z-test. Why can I use a z? Because it's proportions. Proportions, you can use a z-test. A two-sample, or you could call it a two-proportion, okay, either way. In fact, your calculator refers to it as a two-proportion z-test. A two-sample z-test for P1 minus P2. P, remember, is the variable we use to represent proportions. And we just have to decide which way we're going to subtract. What's our P1 going to be in this case? The yawn seed, how do you want to label it? Instead of 1, what do you want to call it? P, I think, does Y make sense? Yawn, or S for seed, whatever makes sense to you, you can do in your test. I mean, it's not a magic variable. Okay, minus the proportion with no yawn seed. So you could write S and N, that's fine. So that's what we're actually, those are our proportions. The best guess we have is our P hat for the yawn seed is 0.294, and the p hat for the not yawn seed is 0.25. And the difference, p hat yawn minus p hat not yawn, all you're going to do is subtract those values, 0.294 minus 0.25, which is 0.044. So does there appear to be a difference in the proportion of people who yawn given a yawn seed versus no yawn seed? There does, a 4.4% difference. Our question is that a significant difference? Is that difference statistically significant? So we need to do a test. We're going to do a 2-sample z-test. Let's write down what our hypotheses would be. Our null hypothesis would be that the difference between having the yawn seed and not having the yawn seed, their proportions would be equal to what? 0. It doesn't matter. The same number of people in a room, the same proportion of people in a room are going to yawn whether they're given a yawn seed or not. That's always the null. There is no difference. Whenever you have a 2-sample or 2-proportion test, you're comparing 2 things, before and after, 2 brands, with and without. So the null is always that their difference is 0. This means no difference. Doesn't matter. And then the alternative, what do we suspect? Is this going to be greater than or less than or not equal to 0? What do you think?
Greater than.
Okay, yeah, does it?
You're saying how many,
The main question was, is yawning contagious? Okay, that was the first question. What do you presume would happen? Why when they say is yawning contagious, what does that mean? People are going to yawn more when they get a yawn seed, right? So if someone yawns in front of you, their suspicion is that, hey, more people are going to yawn if someone yawns in front of them. So we are basically asked for greater than.
Should we write P hat or should we write P?
Oh, you're right. We should not have the P hats there. It should be no hats. Thank you, Alexis. All right, always the true value in the hypotheses. So, all right, so we're not going to, the test is actually all done for us on the next page. So we're just going to go through, and these are the formulas and where they come from, and we'll review those, but these are the formulas for the mean and standard deviation. So in most cases, we do not calculate p-values with a simulation. We didn't. I just opted not to do the simulation here. Instead, we use the sampling distribution of p hat 1 minus p hat 2. Just like inferences for mu 1 minus mu 2, they depend on the distribution of the sample mean difference. So for p1 minus p2, it depends on the sample differences. So the mean of the differences is p1 minus p2. And the standard deviation of the differences is the sum of the variances, square root of the sum of the standard deviations. Basically what you need to know is this is going to be your observed value in the calculation of your test statistic, or, well, observed / hypothesized value, and this is going to be the bottom. This is your standard error, standard deviation. That'll go on the bottom of your test statistic. So then you have your conditions, and this is just a review of the conditions. If both N1 and N2 are large, then the distribution of p hat 1 minus p hat 2 is approximately normal. And the check is that all of the n times p's and n times q's for both different groups is greater than 10. So now you have 4 of those to check because you have 2 separate samples. But we're back to the n times p for the third condition, large sample size. All right, so now the test is all done here, except we're going to have to do a little bit of the calculations at the bottom of the page, so you'll want your calculator handy. So this should be, you should be about tired of confidence or of hypothesis tests, because we've seen a lot of them, and they're all the same 5 steps. The only thing different is the calculation of the test statistics, slightly different. Okay, so at first glance it appears that the proportion of people who yawn when given a yawn seed, P sub y, is greater than the proportion of people who yawn when not given a yawn seed, P sub n, since the difference is 0.044, which is greater than 0. Okay, it's a difference. And it's a positive difference, so that would mean the first one is higher. So this is possible that the true proportions are the same, and we got this difference due to randomization variability. Why is it randomization variability and not sampling variability? It's an experiment. They designated the treatments that people would get. All right, so to decide, I will conduct a 2-sample z-test for P sub y minus P sub n, and then their alpha is 0.05. And again, you can call this a 2-proportion z-test if you want to. Okay, we already have our null and our alternative hypotheses, and then we check the conditions. So for an experiment, there's really only 2 conditions. Were they randomly assigned, and was the sample size large enough? If it's not an experiment, then you have to check to see if it's independent, so less than 10%. And if, again, if you accidentally check that, you'll be fine. All right, so were the treatments randomly assigned? It's not stated, but so we're going to assume that they are. And are the sample sizes large? Well, N of the yawn seed, there were 34 people in the yawn seed, times 10 out of 34 who yawned, so that's 10. And the 34 in the group that yawned, and 24 out of 34 did not yawn, so that's 24. And then N for the other group is 16 times 4 out of 16 gives me 4. And 16 times 12 out of 16, 12 out of 16 didn't yawn if 4 did. So a little note here, not all of them are greater than 10. This one is not greater than 10, so we're going to proceed with caution. Our sample size is maybe not large enough to give us valid information. Okay, so we're using p hat instead of p because we don't know the value of p here to check our conditions. All right, so calculations. Now we're down on the calculations. And when we're performing a test for the null, means the 2 proportions are the same or their difference is 0, we're assuming that the population proportions are equal. However, we don't know the numerical values of P1 or P2. So to estimate this value, we pool or combine both estimates to create a pooled estimate. And so your pooled estimate formula is up here. So your pooled estimate is you basically take N1 times P hat plus N2 times P hat, which we actually calculated up here. So our first sample was the yawn seed. That worked out to be 10. The second one was 4. And then divided by the total number of people in the sample, which was 50. So our P hat pooled would be 14 divided by 50, which is 0.28. So our P hat pooled is 0.28. And that is what is used in calculating the standard deviation. Remember when we did our tests, some of our tests a while ago when you had the option to pool? Yes or no when I showed you on the calculator? We're pooling now, but you actually aren't going to use that same command, and your calculator will just do it for you. So if you were going to do this calculation by hand, the standard deviation uses that pooled P, pooled proportion, in calculating the bottom of your test statistic. So this is the test statistic for a difference of 2 proportions. So for our sample, we'd have the difference in the sample proportions, the observed difference, which would be 0.044, minus, what's the hypothesized difference? 0. All over the square root of, basically the top of each of these will be the same, so it'll be like 0.28 times 0.72 over, in the first group we had 34